So in yesterday's class, we just had a broad discussion on how the MOSFETs behave like a switch, how they can be used as a switch in a VLSI circuits, the N MOSFET and P MOSFETs. Okay. Today we are just going to give a very very brief introduction about how these devices are fabricated. Okay. Now if you see here, there is one full course known as an CMOS technology, in which each and every process is discussed in detail. So this is just summary of that one full course, put it into one lecture. So we are not going to go that deep, and this is just to give a small idea before we switch on to the circuits from the next class. From the next class, we are going to learn next week. That is today, second part, we'll just see a little bit more about technology. After that, next week onwards, we start the actual VLSI circuit design. Okay, so this is just to give a brief introduction about CMOS technology. Now, the first material, raw material for the fabrication of an VLSI chip is sand or silicon. Okay, so what we do is we take the sand in a huge furnace. It is melted. So it is first the silicon needs to be cleaned so that all the impurities are removed. So we take 99.9999%. So that is the purity level required, because even small impurities will finally result in a bad device which will not give the desired performance. So pure silicon is taken. It is put into a furnace. It is melted, and then you have a small seed that is inserted into the furnace, and by slowly rotating you pull it up. So once you slowly rotate and pull, so something known as Ingot comes up like this. Okay, so this is the first step. So I think I have a small video. So this is known as a Czochralski method of doing it. So you can just watch this, just a few seconds video.
In the Czochralski process, polysilicon is melted in a crucible and a monocrystalline seed is lowered into the melt. The top of the melt is lowered to slightly below the melting temperature of silicon, allowing a crystal to nucleate at the seed. The seed is then slowly pulled from the melt.
Right, it is pulled up. Now this is what the Ingot looks like. So now this is the entire thing. Okay, then it is first it will be red hot, and then once it's cooled, then you cut off the edges and then polish the surface like this. Okay, so now these are all silicon cylinders, and then with the diamond wire cutters you cut these into small chips, like small wafers. Now this is a wafer into which there will be several small dies will be there. Okay, so that is the first step here, and then these are the equipment. So over the years, we in the very first class we discussed the size of the wafer also has increased. So these machines, if you see, modern day machines are very huge compared to those which were available in the 1970s. This can pull up close to 400 kg of silicon bar from here, right? So these are the huge ones. So in fact, in 2017 we had one which weighed several hundred kilograms, and then it had 18 inches of diameter. Okay, and the length was close to 3 meter. So this is the first step to create an silicon wafer. So this is the first step. Once having done that, then the other processes start. Now in the substrate, there are few considerations. Now whether we should take P type or N type. Okay, so generally we prefer P type, because the P type dopants they create a minimum of structural deformities. So that is the why. And also because earlier when we said in the first class, from the BJT, when we migrated towards CMOS, even before PMOS came, NMOS was the first device which was invented, and we had chips which were NMOS based. So the technology, so you need for the NMOS devices, we know we require a P substrate. So subsequently only the PMOS came into the picture. So initially one or two generation of ICs were made of pure NMOS. Okay. So that is the reason we have a P-type substrate resistivity, and then we generally have substrate doping of this order, 10 to the power of 15 per centimeter cube. Okay, so we know that if you increase this doping level, then the threshold voltage increases. So in last class we saw that the doping level of the substrate has a major role to play in deciding what will be the threshold voltage. So it is kept low. If you keep it very low, then the leakage current increases. So this is a trade-off between leakage current and threshold voltage. So this is generally kept at 10 to the power of 15. And then you have crystal orientation also. This also will be covered in depth in the PMMD class. You have a crystal orientation. In the way in which these silicon, they are all they have 4 electrons in the valence band, so they share this one electron each with 4 more electrons, and then they form a structure. So the crystal, the axis at which we cut it, okay, so there are different axes, 1 1 1 1 0 0 and all. So 1 0 0 is preferred because that gives the least imperfection. Okay, so these are a few things which you should know with regards to VLSI technology. Okay, now all these fab labs are classified as clean rooms. Okay, and there are several measures to measure the cleanness of a room. So ISO 14644 standard, that is the general thing which generally people use to classify these clean rooms. Now you have ISO 4, which is known as class 10, or ISO 6 class 1000, like similar various classifications are there. And what it means is, if you see here, ISO 5 means your particles more than 0.5 micro size. Okay, it should not be more than 100. So here you will find maximum particles. It is written maximum particles. So for an ISO 5 clean room, more than 5 micron particles should not be more than 100. More than 3 micron particles, it should be somewhere 100. It is say 500, close to 500. And greater than 0.2 micro, it should be less than 1000. That is for ISO 5. Now if I talk about ISO 3, it will be more stringent. Okay, more stringent means if you see here, greater than 2 micro particles is between 1 and 10 only, right? And between similarly greater than 0.5 micro, it should not be there at all. So that is the what ISO 3 means. So that is a very stringent clean, highly high standard clean room. So these are various standards or way of specifying the clean rooms. Okay. Now in the fabrication of CMOS, lithography is one of the most important procedure. So how a lithography is done, we just go through some of the basic steps of lithography. Okay, so once you have an substrate, okay, then you grow silicon dioxide over it. Okay, now so how to grow silicon dioxide is, we'll see that oxidation process. Either we heat it and pass oxygen or steam. So this reacts, that oxygen reacts with the substrate, and you have an silicon dioxide layer here. Okay, once that is done, you have a spin coated photoresist. Okay, that means through a spinner you paste and photoresist. So you have substrate, silicon dioxide, on top of that you have an photoresist. So there can be now two types of photoresist. One is known as positive photoresist, okay, and one is known as negative photoresist. Okay, so they are essentially different chemicals. Okay, now the photoresist, for a positive photoresist, if we expose the area with ultraviolet rays, okay, they become soluble. Okay, and the non-exposed areas remain hard. That means for a positive photoresist, once you are applied the photoresist, they are hard, So wherever we want to remove the photoresist, so we are going to put the ultraviolet. So that where all which area requires to be exposed and which is not to be exposed, for that we use a mask. Okay, so there is a mask through which the ultralight is. So in the dark areas it will be opaque, so no ultralight will be passing through the mask. Whereas you have transparent areas also in the mask through which the violet rays passes. Okay, so now if you see here, the minimum small boxes. This is a very simplified box. You can imagine in this mask there will be several hundreds of small areas. Okay, small holes through which the light will pass and light will not pass, and it is that particular definition which decides the technology. That also plays a big role in deciding the technology, right? So how the smallest holes you can make in the mask. Okay, they define the technology, whether it is 45 nanometer, 190 nanometer, and things like that. Okay, so this is mask. So once it is exposed, you will have these exposed ones and the unexposed ones, and then you can you use a soluble photoresist. Okay, that is known as the developer. So when the developer liquid is used to clean away which is not hardened, so, right? For a positive and negative, the developers will be different, and accordingly some portion of the photoresist will be washed away. Right now, if you see here, after having washed away, you will remove the photoresist, and that so the photoresist essentially what it does, it saves wherever it is hardened. Below that silicon dioxide will be saved. Okay, so you remove the photoresist developer, and then after that you try to etch away the silicon dioxide also. Now once you etch away the silicon dioxide, because the photoresist is available there, wherever it is available here, that silicon dioxide remains safe, and wherever the silicon dioxide is directly exposed, that gets etched away. So you have a now kind of a window opening up. You have a substrate, you have silicon dioxide, and in between you have silicon which is exposed to the atmosphere, right? So now you have this, right, substrate, and you have a photoresistor. Here it is been etched away. Now you can do either diffusion, ion implantation into this region. So when you do that, obviously the silicon dioxide will not allow these ions to penetrate through. Only where the silicon is exposed, there it will get these dopant items will go, and that will turn that much area either into N plus or P plus, depending on the what kind of dopants we are using. Okay, so these are the 6 steps which are used in lithography to dope the required area in silicon in the substrate with P-type or with N-type dopants. Okay, so this is one step. And then over the substrate also a similar lithography process is used, basically for development of the gates. Now you see a substrate is made out here. On the substrate there is silicon dioxide here, and then you have an photoresist. Okay, photoresist coating. And then again you do that ultraviolet rays is passed through a mask, so that the unwanted area gets dilated, and the ones which is required, wherever the photo is required, that remains hard. So once that is done, then you remove the photoresist. So wherever the hard photoresist remains there. Okay, and then after that you remove the then you can deposit the polysilicon there wherever. Okay, so on top of that, so final polysilicon pattern can be done. So you deposit a silicon substrate here, silicon dioxide, then you put an polysilicon, and then a photoresist, right? So here above the substrate we are speaking, that means because initially the gates were made up of polysilicon, and subsequently now for these days we are using aluminum and other metals. So the earlier days polysilicon was used as a gate. So you had a substrate, silicon dioxide, polysilicon, and then on top of that photoresist. Okay, then you expose, remove the unwanted photoresist wherever, and then you etch away the polysilicon. So wherever this photoresist is going to protect my polysilicon wherever is required. So that photoresist, hardened photoresist should be available wherever polysilicon is required finally. So if I am going to use this polysilicon as a gate material, so polysilicon can be used is generally used for gate contact. Now if you see here, this is substrate, oxide, and then polysilicon, and here the polysilicons have been removed. So you will make source and drain implants here later on, but this polysilicon has remained here because you have put this photoresist on top of this. Okay, so these are the various steps which are involved in lithography, right? So if we now start with VLSI fabrication steps, these are the 8 steps which are to be there in the VLSI fabrication, chip fabrication thing. So so first is crystal growth, photolithography, oxidation, diffusion, epitaxy, ion-implantation, annealing, and metallization. So mask is clear type or opaque type for different. You actually mask, whether it is clear or opaque, basically that depends on whether it is a positive photoresist or a negative photoresist. Okay, so for a positive photoresist, if the light is light falls, it's written here, right? Here for a positive photoresist, exposed areas wherever the ultralight that becomes hardened, and it becomes for positive photoresist, exposed areas become soluble and non-exposed remain hard. For negative, it is the other way around. So the masks are accordingly created, right? So these are marks are created through laser beam, so molecular beam cutting and laser through laser cuttings. Okay, so once there will be several masks in the process. Around 6 to 7 masks will be used, and that mask is designed once you make a schematic, and then a layout is decided. So based on the layout, for each process a different mask will be made. So each process will have different masks. Okay, that we'll see now. So these are the various fabrication steps involved in VLSI. So one is oxidation, so you have wafers placed here, several wafers placed here, and here. What we do is we pass oxygen out here and heat this chamber. Okay, now the silicon and oxygen, they react and form silicon dioxide. So this is known as dry oxidation whenever we are passing oxygen. Again, mind you, so when we do oxidation also, only few areas will be exposed, because there will be a lithography which will be done here. So not that on the entire wafer you are creating oxygen. Okay, so wherever required oxygen. So so that we'll see in the CMOS process later on. So now wherever this area is exposed, the silicon is exposed here. Okay, in those areas, that silicon will react with oxygen and silicon dioxide will be formed. So if you are passing dry oxygen, then it is known as dry oxidation. So for dry oxidation, you require higher temperatures, and it takes more time for silicon and oxygen to react. Okay, so it is slightly more time consuming process. The growth of the oxide is slow, but it is grown with lesser imperfections, and it has had, then that's the reason why it has got a higher breakdown voltages. Whereas if you are going to use steam, you can use slightly lesser temperatures and the growth will be faster. So this H2 and these things, they act like a catalyst, and the reaction is much faster, but the quality is not all that good. Okay, so not for the oxide Yeah, see the oxides will be used in like we will be putting oxide, removing it, putting it again, okay, for various implant regions. So when we are making the oxide just below the gate, there we would prefer dry oxidation. But when we are doing, say, trench isolation, right, in those cases we can have wet oxidation. So it depends on what purpose, what is the where we are doing the oxidation. It depends on that, what kind of oxidation we do. Okay. Then similarly we have diffusion here. Then the vapors are kept here, and then you have an inert gas. Inert gas is a gas which won't react with silicon, and you have this donor, the molecules of which needs to be implanted, kept separately and preheated. So when the carrier gas they move, they pick up these molecules, and they are here also there will be windows cut. Okay, only in those areas these items will be diffused. Okay, so please do remember, so in each of these process it is kept after photolithography. So it is not that these molecules go and sit all over the surface, only wherever it is exposed. Okay, so for all this process, before we do the diffusion, the proper masking is done. Okay, lithography is done, and windows are cut open where these things go and get deposited. Okay, so that is known as diffusion. Okay, and then you have something known as epitaxy. This is slightly initially we said on the P substrate, and we make a small source and drain regions of N. Okay, but nowadays because of the high performance requirement, we generally we take a wafer of silicon, and on top of that again grow a very thin layer of high quality silicon. Okay, that is known as epitaxial growth. Okay, it is not necessarily you grow silicon, you can grow like now you have silicon germanium also, right, channels, right? Silicon germanium or pure germanium. So those times on the substrate you can have, so that substrate is heated through an electron gun, a high reflective electron gun. So that heats up the substrate, and then you can have these molecules which are required to be deposited being projected through the effusion cells. Okay, so you could have silicon and you could have germanium, or you could have both of them in a and you can control the amount of silicon germanium which is being thrown onto the wafer, so that you have an silicon germanium, required silicon germanium concentration, right? So if you see, when silicon and germanium both are used together, they create a little bit of stress in the lattice, which in fact increases the mobility. Okay, so that also probably you will learn in your CMOS technology classes in detail. So I am just giving a rough idea. So this is what an epitaxy chamber looks like. So this is an epitaxy chamber which is shown on the right hand side. Okay, now this is how different gases are thrown, and they react, and they create a silicon layer, or they can create germanium also, or you can have even silicon germanium also. You might have to dope it to keep it slightly on the towards the P region or the N region. So you have these several windows, right? So the required molecules needs to be projected onto this okay, silicon, germanium. Say if you want boron and or phosphorus, those also can be done. So they react and they create the epitaxial layer. Okay, that is known as epitaxial growth. Okay, okay. Flick's law of diffusion. Okay, that gives the rate at which the growth happens. Okay, so it says if there is a higher density of items being flowing here, and the velocity, so it is proportional to that. Okay, that just the Flick law says the amount of the flow of the items that requires to be deposited. So and also the density. Okay, so obviously it will be directly proportional, right? If you have high density ions passing here, then the growth will be higher, more atoms will get diffused, and similarly if the rate is high also, then also. So it depends on rate as well as the total concentration. So these are known as the Fick's law. Okay, so this is not actually very much part of your VLSI class, but we are just touching upon this topic so that when we start designing VLSI circuits, and this gives us a slight idea of what's happening in the background. Okay. So we talk about epitaxy. Then we have ion implantation. Like in a P substrate, we have so we are going to make a source and a drain region, right, with N plus. So what we do is we generally use ion implantation. And what is ion implantation? So the source ion is placed here and it is heated up, and through electric field it is accelerated. So now you have one ion magnetizer here and an ion selection aperture here. Okay, what they do is see, if there are impurities here, okay, those impurities will not follow this path, because the mass of that impurities will be different. So they are so arranged that only the required ions, the one which we actually require, say I want to implant boron, only the boron will flow through this small aperture and come out, whereas if there are some other impurities also in the ion source, they will not converge here, they will go and hit the walls out here of this chamber. Okay, they will not pass through and through. So that is passed here, and then you have a lens assembly, X and Y plates, that is to scan this beam in the wafer. Okay, so if you apply potentials on the X and Y plates, you can this impact point can be moved anywhere on the wafer, right? So that is how we do the ion implantation. So this is known as an ion implantation. So this is an ion implantation chamber, which it looks something like this. So after the implantation, if you see here this black dotted line, okay, once you implant it, on the x-axis is the depth from the surface, okay, and on the y-axis is the concentration of the implanted material, like for in case boron concentration if you have. So once I do the implantation, you will find which is very close to the surface, slightly away here, you will have maximum boron concentration, and it falls very steeply as you move towards the inside of the wafer. Okay, so that is not an desirable characteristics. Okay, I should have an boron spread, that region, the entire region should work like a single N plus region, or a P region, a P source or a P drain. So what I do annealing. Annealing is nothing but keeping it at a high temperature for a specified duration of time. So if you see here, this orange, the last one which is here, so greenish color thing, you heat it up to 1050 and keep it for 90 minutes. Then whatever was implanted towards the which was there in the got concentrated towards close to the surface, gets evenly spread out. Okay, so after every implantation, we need to do annealing. Annealing is nothing but heating the chip wafer to a specified temperature and keeping it in that condition for a specified duration of time. Okay, so this is known as annealing. Now finally we come to the CMOS process. We know how an CMOS device looks like. So this is an P substrate, right? Then you have an this is actually, like I said, there is an epitaxial P which is developed over the P substrate wafer chip. So this is what today's technology, you have an epitaxial P out here, and then you have this NN and this is the channel region, so you have a gate here, and for an PMOS you have an N well here, then you have a PP being doped here, so the channel remains N, and then you have a gate connection, source drain connections. Okay, so this is what is our final chip. In the final chip we need to have these kind of devices. So how to go about doing that? So this is the starting process. So the first starting point is having a wafer. Generally wafers are 75 to 230 mm in diameter and less than 1 mm thick. Okay, on that you develop a clean silicon P epitaxial layer. Okay, now what is epitaxial? If you go back here, what we did here, like we are pumping in these silicon chloride and hydrogen, so they react, and then you have silicon getting deposited and HCl, that is the gas which would come out. Okay, so you will have UV chamber, silicon hydrochloric acid, and then you heat up, then silicon starts getting deposited here. Now I want a P substrate, so I can put in some boron also here in limited controlled environment, so that whatever is deposited is P-type epitaxial. Okay, so that is what is being done here. So you have a P-type epitaxial growth. Okay, so this will be there will be you can see, because of the process itself, it will be very pure kind of silicon layer without any deformities. Okay, because when you make here you are melting it and pulling it up, this may not be structurally as defect free as an epitaxial. Okay, epitaxial is a much better option available. So once you do that, then we make an N-well mask. Okay, N-well mask is this is in the entire chip area. Okay, we define this is the area in which all my PMOS, several PMOS, there could be hundreds of PMOS. In this area I am going to put my entire PMOS. Okay, so I make an the mask. So the first mask is going to be an mask. This is the top view of the mask, N-well mask. So you put that mask out here. Yeah, is done. See, diffusion and ion implantation are two different things. You can either use diffusion or use ion implantation. These days we use ion implantation only to implant. Okay, diffusion is not used. Okay, so you find here, now this is the mask. So you have an epitaxial layer out here. So first you will put an silicon dioxide layer, then you will put the photoresist lithography, then you will use this mask, and you will clear that photoresist, and after clearing the photoresist you remove the silicon dioxide. So this is the active, this is not N-well, don't think this N-well is only for one PMOS, this is the entire well for several PMOS of your entire chip. Okay, so silicon dioxide, then we put the mask here and we remove the mask from this where we want the N-well to come up, right, and then we remove the silicon dioxide, and now this is ready, this area is now ready for to be made into an N-well. So now we can do ion implantation. Okay, so ion implantation, now the advantage, like who was it? Aman Jain had asked, right? Probably why not diffusion, why implantation? So ion implantation is more controllable because it is through an electric field, and we are accelerating and pumping the electrons. So we can actually keep the depth, we can control the depth in a much controlled manner when we are using ion implantation rather than diffusion. So using ion implantation, I am going to make an N-well here. Basically I am going to put a phosphorus, right? Phosphorus, I am going to implant phosphorus, so this entire area becomes an N-well here. Okay, so that is the first one mask I have used out here, right? And once that is done here, now this is P, so I don't have to make a P well here, right? And this is N, that is also is already now made. Now we said between the P well, P where all the NMOS are kept, and the N well, we need to have a separation so that the latch is not formed. We discussed the latch yesterday, right? So we need to make trenches out here, okay, or we can implant P plus, so that is P plus rings. Okay, so what do? Again we put an oxide here, and we put an on top of that photoresist or silicon nitride. Now if you see here, oxidation happens in many steps. So in these steps you can use wet oxidation, because finally these are going to be again removed. Okay, so wherever, so now you have put an oxidation, and you have put an photoresist on top of that and removed the photoresist, and then now here we are going to pump in P plus or rings, okay, across this. So that is done here. So that is the area, active area definition. That means we are safeguarding it. So that can be done here, right? That's known as isolation. Active area, we said that we already implanted in the N well. We have formed an N well there. Okay. Now isolation is like you have forming of an P plus ring across the P where area where we are going to make our NMOS. So we implant a boron, which that will become an P plus ring. So that is, so one more mask will be consumed here, right? So there are different masks for each step. Different kind of masks will be made. Okay, so you can do that isolation, or you can also use channel stop. Okay, what is channel stop is, you can have an instead of having a P plus ring, you can make a silicon dioxide. So here also this area is exposed. Now you have you form an oxide layer, then you put a photoresist here, you put a photoresist here, and then again you try to oxidize it. Okay, now more and more silicon here, which is there in the wafer, that will keep getting consumed, because that starts become silicon dioxide reacting with the air. So this will go deep here. Now this is known as an local oxidation here. So this separates the N well from the other P region. So you can use this technique also. So this is like, it keeps once you do the oxidation, the silicon it is exposed here, right? The silicon is exposed, and when you do oxidation, not only silicon dioxide deposits on top, it also goes to the bottom also. More and more silicons in the bottom, towards the bottom also, they keep reacting with oxygen. So you will find that this kind of isolation wells can be formed by oxide. Okay, so in short, oxidation is not just growing oxygen on top of the silicon layer. So these kind of, when you do oxidation for a longer period, the oxidation grows into the silicon wafer also, and that we can use it for as trench isolation. Okay, so after having done that, now we need to make gates. Now you have made an N well, and you have an active P region, right? Now it is not that source and drain is made first and then you put an gate over top. Okay, it is the other way around. First we make the gate, okay, and then we may diffuse the source and the drain. So the advantage of making the gate first is, so this gate, once you suppose I am going to make this a NMOS, I put a gate first here, and then I implant N materials. So they'll get, Saurav, correct. So they get self-aligned. Okay, so you don't have to worry about the alignment aspect. So automatically in between there will be a channel, and on the both sides you will have a source and drain. So that is known as self-aligned. Okay, so you make an polysilicon. Again the procedure is same. So again you will use one mask wherever you have decided to put gates. You will first you have silicon, then you deposit a polysilicon on top of that, then you put an you will first put the entire polysilicon gate all over the place, then you put an photoresist, then you remove the photoresist wherever you don't want polysilicon, and then again you etch away all the polysilicons. Okay, so this photoresist will prevent the polysilicon getting etched away wherever required. So wherever there is a gate, that polysilicon remains there. Okay, so now you have one more mask being used here, right? Okay, once that is done, the polysilicon is there, okay, and then you have one layer of photoresist put here, because the kind of dopants which is required for N well, these are P, right, P source and P drain. So you have to safeguard this area. So you put an entire photoresist you have put here, okay, it is exposed. Now this is exposed. Now you put the P type impurities, right. So now this will become P source and a P P source and drain, right. So this is known as a P plus mask again. So one more mask has been used here. It is self aligned process, okay. Now you will find that certain amount, when you are doing it here, certain amount of when after that we need to do little bit heating also, so that they are aligned, so that they are spread evenly. Some amount of here you have acceptor impurities will come below the gate, okay, that is known as overlap, okay. So some overlap will be there below the gate also. There will be little bit of source and drain, okay. So that gives rise to other issues which we will discuss when we are discussing the MOS capacitance, okay. So this is how it is done. So that is known as the P plus mask, and then you have the N plus mask. Now you cover this entire active N region, and wherever we want to have an N for the NMOS source and drain, so small holes are cut there, and through those holes and we are going to put arsenic or phosphorus, okay. Here so here boron, we generally use boron for the P, and here we are going to use arsenic or phosphorus. So this is our NMOS. So you have one more mask which is coming in here, okay. Now after that annealing, which I said, which we are going to heat it. Now once you heat it, you will find this gets slightly diffused below the gate area also, okay. So you have, so the effective channel length will be slightly lesser than the channel length you have put here for the gate, okay. So the actual length will be slightly different. So if you are using say 100 nanometer here, so it will be close to only 90 nanometer here, okay. So this channel length, so it will be slightly, the effective channel, that is known as L effective. So L effective will be slightly the source and drain will be self aligned, okay. So this is known as annealing process, okay. So once that is done here, now the contacts needs to be taken out, right, from the source region and from the drain regions. So again you have one more contact mass here, right, and then you grow silicon dioxide, okay. First, if once you have made this source, and then again you make the entire silicon dioxide using a mask. Wherever I want contacts, I again cut open, and then I deposit metal, okay. Now this metal is generally deposited by chemical vapor deposition, like again it is heated, and say if I have to make an aluminum, so some aluminum mixture with some other gas, it is reacted, and then aluminum starts getting deposited here, okay. So wherever there is a hole, it will get deposited, and then it will make an contact. So that is known as contact. Now once one metal layer is made, again you will have one more mask, and you will put one more layer of insulator, and one more, the third metal layer, second metal layer, third metal layer. So there will be several metal layers. So accordingly the requirement of mask will go up, because if you have to pack these transistors densely, you can't have a single metal layer. There are hundreds of transistors, each requires to be connected with each other, and if you are using a single metal layer, they cannot crisscross each other, okay. So we use multi metal layer. What is multi metal layer? You have a metal layer, then you have an insulator, on top of that another metal layer. So metal 1 and metal 2 can run along and crisscross each other or run parallel to each other. They don't get connected to each other, okay. Only wherever there is a requirement, there we put a wire and we do an interconnection, okay. So the resistances actually the resistances are negligible in today's technology. So we can assume that most of them are same. Only thing is when we design and layout, depending on the current which we know is expected to flow in a particular section of the wire in that particular metal strip, there we have to accordingly give the width. Okay, for example, so the yeah, it is mostly like that. The bottommost layer is the best metal. As you go up, there will be some. So, but the thing is, what is more important out here is, suppose I have to give, I have to just interconnect two gates. Okay, so I need not use a very thick kind of a metal wire, but suppose I have to connect one drain of a transistor with source of another transistor where we are expecting a few micron ampere currents to flow, then we might have to use a metal layer. So when we do the layout, you have to ensure that the thickness of the metal is good enough to sustain the currents. Okay, so that part we need to take care. Okay. So many a times because for small circuit manually if we give a preference to one particular metal, okay, so it will be very difficult. With millions of transistors, okay, it will run, the software will run an algorithm and try to make whatever best possible. The target is not to keep the use one particular metal. The target is to reduce the overall chip area. Okay, so this is again metal to formation, and once that is done, we protect the entire chip by a layer of SiN. Also acts like an which it prevents contamination of the chip. So this is many a times SiO2 also can be used, or silicon nitrate also can be used over and above the silicon wafer, so that it doesn't get contaminated later on. So these are a few sequences which we follow in CMOS fabrication. Okay, so we'll take a 5 minutes break, and then we'll continue from here. Okay, thanks a lot. So every fab lab, okay, depending on the technology they are using, they given they specify certain design rules which the software like Cadence and other, where when we make the layout, they are incorporated as DRC, design rule checks. Okay, essentially why you need to have these design rule checks is, like when you are doing the patterning, so there will be certain limitations, right? The minimum amount of windows which you can cut, and also the spacing between two lines, because during fabrication it is not that on the metal might get deposited in an exactly straight line. So there will be some tolerances will be there, and those tolerances, if the wires are too close to each other, and because of those tolerances they might ultimately short each other. So all those things needs to be taken care of to cater for all those imperfections or tolerances during fabrication. Certain rules are set. So these rules, if you follow, it will ensure that your final device which is made will be free from fabrication errors. So if you don't follow these rules, then there could be a possibility that your final design may not work at all. There could be unwanted connections made here and there. Okay, so you have a certain parameter known as lambda, okay, which is generally equal to L by 2. So the basic most of the design rule is specified in terms of lambda. Okay, now we'll see that. So lambda is generally L by 2 here. Now for example, when you are making a metal length, when you make a metal connection out here, okay, so the minimum width of that line is given by 2 lambda. Okay, so that this distance that is specified as 2 lambda. For different process it will be different. This is just an example for a particular fab lab. Excuse me. So this is 2 lambda. Similarly, because if you go beyond below 2 lambda, in some places it can happen that this is not a perfect line and there is a cut somewhere, and that can result in discontinuity, right. So to cater for that discontinuity and abnormalities, the minimum width is specified as 2 lambda. So if you use 2 lambda, you can be sure that this entire, whenever you get fabricated, there will be a positive connection between these two ends. Okay, so you have to use minimum 2 lambda, so that even with small deformities there will be a positive connection. Okay, and this also doesn't mean that for every line you are going to use 2 lambda, right. So that is the minimum thing. Now if you have to if you envisage higher currents which are going to flow in a particular section in layout, you can use it in thicker wire layer also. Okay, so that is also possible, and that you should do in fact. So all your VDD rail and ground rail, you should make it in a pretty thick, because through those rails high currents will flow. And also there is a minimum spacing rule also. So when we make when we are running two metals of the same metal 1 and metal 2, they can run parallel to each other because there is an insulator, so it doesn't matter. But when you are using, say, metal 1, 2 wires are running like this, so there has to be a minimum spacing here. Generally it is around 6 lambda, this spacing between 2 here. Okay, so those things will be specified by the fab lab. So it is not an universal law that it should be 6 lambda or 2 lambda. So from fab lab to fab lab, those things will change. Okay, similarly when you make contacts, right. So in contacts, if you see here, if there is a source region, you make a small hole here, and then you deposit aluminum to get a contact. Okay, so that dimension of the hole is also minimum size is specified. Okay, so that is, if you you can't have a very small thin hole here, right. And also once that hole is made here, and then you have to define an area here like this. Excuse me, because this hole, when it gets fabricated, you will find that it may get fabricated here or here. So these clearances also needs to be maintained to cater for the imperfections. So all those dimensions are given. So for most of the VLSI engineers, what happens is, especially for MOSFETs, PMOS, to make things simple, each of these device, the manufacturer provides the because these are all very critical, the manufacturer provides the layout directory also. So when we call for an NMOS in the schematic, and then we make a PMOS, we take an PMOS layout, right. We are not going to draw the PMOS starting from the active region and also all these small issues will be taken care of, and then all that we need to focus on is the interconnection. Okay, so that is what generally VLSI engineers do. Similarly, now if you see here, this is the N active area. This is the mask. Okay, and this is the N active. So this is the N active where all the PMOS is being made, right. So we just now a few minutes back we learned that first we need to cut a hole and make an N active area. So so the mask will be the outside one. This is the dimension of the mask, which is known as N select, and this is the active area. So you have to cater for, because on the edge of the mask, not necessarily just below, on this edge an active area will be formed when you are doing an implantation, right. So you will find excuse me, so we will not define like active area and bigger than the mask window, expecting this to get diffused towards the end. Okay, so that will result in a low quality device. Okay, so if this is the mask cutting, okay, then we cater for this much. Okay, this is going to get wasted here, and that is known, that tolerance we take it here, and we define the active area this much. So we take a bigger mask end select. End select is the mask cutting which you have here, and this is going to be the active area. So these are some of the design rules. Okay. Excuse me, got a bad throat today. Okay. Similarly, when you have a channel here, when we make an gate over it, okay, when you are making a polysilicon, so the width of this defines the length, right? And then this is the width which defines the length of this is the source, this is the drain, and in between you have the length. So you have the gate out here. So you have to put a gate here which is extending beyond the source region and the drain region here for this channel, the entire channel to be controlled properly by the electrostats which is given on to the gate region. You can't have a gate like this, okay, because coinciding with the edge of the channel here. This is known as no overhang. So there has to be limit. This how much overhang has to be there, that will be specified by each design fab lab. Okay, so here we are ensuring that if this is the length, the entire width here is properly used as a channel. So if you see here, then there may not be good electrostatic coupling at this edge, okay, towards the end of this gate region here. So this is no overhang, so this is not permitted. If you use something like this, then your entire device is gone, right? Because this will result in a short circuit between the source and a drain. When we do, because we grow a poly and then we do the implant from top, right? So if this get misaligned, then you will get the entire thing, drain and source, getting short circuit. So these are some of the design rules. So you don't have to memorize anything. This is just those who are working on layout, they will know. So the software checks for all these imperfections when we have design, and it will suggest us to do the necessary corrections in the layout. Okay. So similarly, you have an the other processes. Okay, so that's about the design rule checks. There are certain other processes which we discussed in the first class, I said. So we can have an N plus region and then a P well here, right? So these kind of double wells are also used where you want to have a separate body connection. So you can have this twin well process, like this is a twin. You have an epitaxial layer, you have an N well, and you have an P well. So these are some of the processes which are used in modern day. And then this is silicon on insulator. Okay, again, instead of an epitaxial layer on the wafer, we have a sapphire. Okay, sapphire is nothing but a glass kind of thing, right? So it is an insulator, and then after that we deposit small epitaxial N plus and P. We grow now this P channel is also grown epitaxially. You have an insulator in the bottom, so there is absolutely no body effect at all. Lot of stray capacitances are avoided. You don't have issues like latch and all things like that. So this is a technology which is now thin. It's known as a thin oxide. You have this thin film fabrication process. So this is now the one of the latest trends which is used in fab labs. Okay. So silicon, like these are some of the advantages. You have no wells and a lower substrate, lower leakage currents, and you don't have this latch up issue, body effect issue. So these things are not there in the SOI technology. Okay. And then these are some of the process enhancements which has happened over the years, and several metal layers have been now, instead of having one or two metals, you have several metal layers. So copper is used to wherever there is a requirement of reducing the resistivity. Obviously gold is extremely expensive, which would have been the best thing, but then somewhere instead of aluminum, copper is much better, although it is slightly more costlier, right? You have so these are some of the things which are now. You also have bipolar transistors like BJT and CMOS also being fabricated on a chip. So that we'll see, because the BJTs have a higher current carrying capacity. So to take advantage of that, you have something known as BiCMOS technology, where the control signals are Generally for the control signals we use MOSFETs, and in the final driver stages you have BJTs. Okay, so you have this bi CMOS technology also coming in. Okay, so with that we come to end of this.